Hi, this is our second video about equilibrium. We're going to now start calculating values of our equilibrium constant K. So I like to follow a few steps when I'm going to calculate a value. First of all, I like to write the expression for K. If I don't write the expression, I sometimes forget those coefficients in the balanced equation. I want to make sure that the concentration units are correct. If it is molarity, it is moles divided by liters. And then I plug the values into the expression. So let's just dive right in and get started. The following equilibrium process has been studied at 230 degrees Celsius. And they give you a balanced equation. Again, remember, whenever you're talking about an equilibrium reaction, they'll give you a balanced equation and a temperature. The value of K changes with temperature, and we'll see how in a later video. So the concentrations of the reacting species at equilibrium are found to be. Now that's important. They're giving you the concentrations at equilibrium. And so you're able to plug the concentrations that they've given you into the K expression. Again, the K expression, you have to be at equilibrium in order to plug those concentrations in. So I'm going to go up here. The K expression is equal to, it is the product, the concentration of NO2 squared divided by the concentration of NO squared times the concentration of O2. Okay, so that's my K expression. Now what I need to do is I need to plug these numbers in. And so the NO2 concentration at equilibrium is 15.5 molar. That's pretty big. All right, and I got to square that. And then I'm going to divide it by the concentration of NO at equilibrium is 0.0542 squared. And then my concentration of oxygen is 0.127. And when I plug all this into my calculator, so it's 15.5 squared divided by parentheses 0.0542 squared times 0.127, I get a pretty big value, and it is 6.44 to 3 significant digits times 10 to the 5th. Now that K is much greater than 1. And so that means that at equilibrium, we would say equilibrium lies to the right, meaning we've got a lot more NO2 at equilibrium than we have of the reactants. And that's what these numbers show as well. We've got 15.5 molar of NO2, and it looks like our reactant concentrations are very low. Okay, so that's how you calculate a K. Now, let's go on and try another problem. All right, we are given a value for K, and here is the reaction. It's hydrochloric acid, and it's decomposing into hydrogen and chlorine, and the K for that reaction is 4.17 times 10 to the negative 34th when you're at 25 degrees. All right, what that means is that there are very few products in equilibrium, very, very few, because our K is so small. Now they want to know what the equilibrium constant is for this reaction, and it's a synthesis reaction. Actually, it's just the reverse of that reaction. All right, so let's go ahead, first of all, and write the K, whoa, there we go. Let's write the K expression for our initial equation. So the K is going to be hydrogen times the concentration of chlorine divided by the concentration of hydrochloric acid squared. Okay. Now how about the K for this reaction? Let's write the K expression for this reaction. K is the concentration of hydrochloric acid squared divided by the concentration of hydrogen times chlorine. Notice the relationship between these two. This is just the inverse of that. See how this K expression, when we flip this equation, the K is just the inverse of the original equation. So what we're going to do for the value of K for this reaction is we're going to take the inverse of the K for this reaction. So this reaction's K, it was very small, 4.17 times 10 to the negative 34th. Now this K value is going to be 1 divided by 4.17 times 10 to the negative 34th. And we come up with actually a very large number, which is 2.40 to 3 sig figs. Oh my goodness, that's a 2. 2.40 times 10 to the 33rd. So in this reaction, there are lots of products that are formed. In this reaction, the K is so small, there's very little products formed. All right, so in summary, if you have a reaction, if you write the reaction in reverse, the equilibrium constant of that reverse direction is going to be the inverse of the equilibrium constant of that reaction in the forward direction. All right, what if you have multiple equations? So we did this with Hess's law. All right, so let's say we have these two equations here. We've got A plus B gives C plus D, and it's at equilibrium, and C plus D yields E plus F. All right, so our first equation, the K for it, this would be K1, would be C times D divided by A times B. Oh my goodness, messy, messy. Okay, in the second equation, this K would be E times F divided by C times D. Okay, now the overall reaction, when we add these equations together, notice the C's and the D's cancel. And we get the equation, the overall reaction, A plus B goes to E plus F. And so the K for that would be E times F divided by A times B. Okay, so if you see what happened when we added these two equations together, this is our overall equation. We're pretty good at adding equations, I hope. And then what happens with the K, it looks like they were multiplied together, don't they? If I multiplied K1 by K2, wouldn't we get E times F divided by A times B? Exactly what we get. So when you are adding equations together, so if your final equation is the sum of two or more reactions, the K for that overall reaction is the product of the equilibrium constants from those individual reactions. Okay, what happens if you multiply an entire equation by a number? What would you do to the value of K? Well, you would raise it to that power that's equal to the number. So if we multiplied an entire equation by 2 and we had a K for it, we would square the value of K. Because remember, those coefficients in a balanced equation are actually the exponents. All right, we're going to talk about one more thing in this video, and it's predicting the direction of a reaction. So here we've got the synthesis equation at 430, and we have a value of K. Now, they give us some concentrations. They tell us the moles, and it's in a 1 liter container. So it's moles divided by 1, it becomes molarity. So it's a molar concentration. We don't know if these concentrations are at equilibrium. So we can't say, well, K is equal to. We're going to call it a Q. It's called a reaction quotient. And what we're going to do is we're going to say Q is equal to the concentration of HI squared. It's set up exactly like a K equation, but when you plug the numbers in, you don't know if they're at equilibrium or not. So let's go ahead and plug these numbers in. Let's see, HI is 1.98 molar because it's 1.98 moles divided by 1 liter. And then divided by 0.243 molar for the hydrogen and 0.146 molar. Now, if I go ahead and calculate this, if this value equals 54.3, it means we're at equilibrium. Okay, so I went ahead and I put it in my calculator and I found out that this value is 110. We are not at equilibrium. So here's what we're going to do. we are not at equilibrium. Our Q value is bigger than the K value. And what that means is this Q, we have more products. That's why it's bigger than what we should have had at equilibrium. So we have, in a sense, gone past equilibrium. So to achieve equilibrium, we're not at equilibrium, it's going to have to shift to the left to get to equilibrium. So this is called a reaction quotient, and it's solved exactly like K, except you don't know if your concentrations are equilibrium concentrations. And then you compare your Q to K. Now, again, in that last problem, the Q was bigger than the K, which meant that we had too many products and we were going to have to shift to the left to restore equilibrium. But you could have the opposite thing as well. You could have your Q being smaller than K, which means we need more products and it would shift to the right. Well, I have kind of an easy way to remember that, but you'll have to explain it. I put my K and my Q in alphabetical order, and so K comes before Q. And then if the K is bigger than the Q, or the Q is smaller than the K, it's going to have to shift to the right to reach equilibrium. And if my Q is larger than my K, which was the case in the last slide, it means I have too many products and I'm going to have to shift to the left to restore equilibrium. All right, that's it for this video. We're going to have one more on calculating values of K, and then we're going to talk about Le Chatelier's principle. Again, I'm sorry, here's just our last final conclusion slide. If K is bigger than Q, you will shift to the right. If K is less than Q, you'll shift to the left to achieve equilibrium. And if Q equals K, you're at equilibrium. All right, have a good